Hi, good afternoon, everyone. Thank you for joining our next session at the H.C. Wainwright Global Investment Conference. My name is Joshua Corson, and I'm an H.C. Wainwright Equity Research Associate. For our next presentation, I'd like to introduce our presenter, Dr. Maria Macchiachini, who is the CEO of Annovis Bio. The floor is yours.
Thank you so much, Josh, and thank you for coming to one of the very last presentations. Today, I'd like to talk to you about our drug, buntanetap, that is in phase 3 pivotal study for Alzheimer's disease. What I also wanted to do is give you a little history of Alzheimer's drug development, and then tell you how our drug fits into the existing Alzheimer's landscape, how it complements it and enhances it. So mostly, I was going to talk about cognition because there is a theme that we can go across, and the same test, which is called ADS-Cog, that goes across all cognitive studies. And so as you can see here, around 2000, there were several drugs that were developed for Alzheimer's disease. They improve cognition. Short term, they're called symptomatic. And then there was a 20-year lull where no drugs were approved. However, in that lull, a lot of research happened. And in the last few years, we had several approvals of drugs that do not improve cognition. What they do, they slow the cognitive decline and therefore preserve cognition. What has also happened in the last 10 years is that a lot of novel mechanisms of action has been tried. And if you look at clinicaltrials.gov, there are over 180 different Alzheimer's studies ongoing right now. So what you're also seeing on the slide is that for the next 2 to 3 years, I'm predicting that we will have novel drugs on the market. They will complement the existing drugs. One of them is going to be ours. They will be disease modifying, and they will actually be easier. They will be oral available, they'll go into the brain, they'll be easier to administer. Because what we need right now are drugs that are safer, that are easier to administer, that are cheaper, and that help a large population. This is maybe a little bit more detail on how these 3 classes of drugs actually look. The original one that was developed before the turn of the millennia was based on the fact that neuronal cells work less. They release less acetylcholine, and acetylcholine is responsible for how we think, how the cell works, and for our cognition. So the treatments were replacing acetylcholine or increasing acetylcholine. That works just short term because the cells get exhausted and they still die. Neurodegeneration means death of nerve cells. But if you make the cells work harder, but don't protect them from dying, they still die. And that's why they're called symptomatic. They increase cognition short term. The novel drugs don't increase cognition short term. What they do, they protect the cells' degeneration. They protect them from dying long term. What I'm showing at the bottom are actually the cursor doesn't work. What I'm showing at the bottom are the drugs that, specifically the drugs I'm developing. What we are doing, we have a drug that improves cognition short term, but also protects nerve cells from dying long term. It is orally available, it goes into the brain, and it does not have side effects. So let me first talk about what happens in the brain of an Alzheimer person. This was already published 10 years ago. In the brain of an Alzheimer person, you have plaque. We all have plaque. Well, not all, but over 40 years of age, a lot of people develop plaque. And then you have tangles. A lot of us have tangles, and we are not demented. However, the Alzheimer brain has more than that. It has alpha-synuclein. It has TDP-43. It may have vascular dementia, and it has a whole slew of other defects. that could have happened when you were a kid and you were exposed to zinc, to lead, to mercury, God knows, to too many carrots. So the reality is that while plaque is a component of Alzheimer's disease, it is just one component. There are a whole bunch of other things that cause Alzheimer's disease. So we are concentrating here on the 4 toxic proteins that cause Alzheimer's disease. One is plaque. We have heard about it. The existing drugs remove plaque. They remove A-beta in a number of different forms. But then there is tau, they're tangles. And as I just said, there's alpha-synuclein and TDP-43. The existing drugs only remove A-beta. Our drug lowers the levels of all of them. So it actually removes all the toxic proteins in the brain. Now, how does it do that? How does one small orally available molecule inhibit 4 proteins? It's because it doesn't act on the protein. It acts on the mRNA. And the mRNA of these 4 proteins has a homologous region that is the exact same region that is responsible for their translation. So the same region regulates how these proteins are synthesized, and our drug inhibits that region. And by doing that, our small molecule can actually inhibit all 4 proteins. So this just shows that, in fact, we do inhibit all 4 proteins. On the very left, you see A-beta. We don't just inhibit APP, but we inhibit all fractions of APP. There is a C-terminal portion, and the A-beta is in the middle, and then there is an N-terminal portion, and we inhibit them all. Then you see alpha-synuclein, then tau, and then at the very right, you see TDP-43. So we are inhibiting all 4 toxic proteins that are in the brain of an Alzheimer patient. Now, I mentioned briefly that our drug is symptomatic and disease-modifying. And it doesn't do it neither by the way the existing symptomatic drugs do it. It does not increase acetylcholine, and it doesn't do it the way the existing disease-modifying drugs do it. It does not just inhibit A-beta. So how does it do it? How is our drug symptomatic? Well, it turns out that neurotoxic aggregating proteins, all of them, they inhibit axonal transport. What does that mean? Well, if you think that your nerve cell's body is in the brain, it has a long arm that goes to your fingers, your toes, your tongue, your heart, your gut. If that information flow is slowed, something doesn't work very well, right? So in Parkinson's, if the information is slowed from your brain to your tongue, you slur your speech. If it's slowed from your brain to your feet, you shuffle your feet. In Alzheimer's, if it's slowed from the right hemisphere to the left hemisphere, you can't think. And that is why our drug actually works in Alzheimer's and Parkinson's. It improves and it speeds up the information flow. And that's shown very nicely in this slide. On the top, you see the arm of a healthy human nerve cell. And if you look at the little black dots, they move very smoothly from the left to the right. In the middle, you have a human Down syndrome nerve cell. In Down syndrome, the speed is reduced by 30 to 50%. And then at the bottom, you have the exact same Down syndrome nerve cell, and it was incubated for 48 hours with our drug. And as you can see, the information again flows very smoothly from the left to the right. Now, how long does it take for this to happen? In our experiments, it takes 48 hours, which means that the speed of your nerve cells are improved in 48 hours, which means this is symptomatic. The speed of your nerve cell improves pretty much right away once you treat with our drug. And if you improve the speed, you improve cognition. Well, why do nerve cells die? As I told you, the first thing that neurotoxic aggregating proteins do, they slow the speed. The nerve cell looks sick. And when a nerve cell looks sick, what happens to it? It gets attacked by the immune system. These are these are microglia. Microglia is the immune system of the brain. And this is in traumatic brain injury rats, where you can hit them over the head, and then you can open the brain and see what does the microglia do. And what we saw is that when you hit a rat over the head, the microglia gets big, which means it gets activated, which means you have inflammation. When you treat with our drug, you see that the bars shift to the left, which means the microglia get smaller, which means it's not activated. So our drug inhibits inflammation, not directly, but it inhibits inflammation because the nerve cells are not sick. And if they're not sick, there is no inflammation. And finally, the nerve cells do not get killed. And why, again, don't they get killed? Because if they're not sick, if the microglia doesn't attack them, they remain alive. And that is the disease-modifying part of our drug. But let me first show you why we know that our drug protects nerve cells from dying. So on the left, you have the same traumatic brain injury rats that I just showed you for microglia. The blue bar shows the normal, healthy number of nerve cells in a specific brain area in a healthy rat. And it's about 5,000 nerve cells per unit. If you hit that rat over the head, half of the nerve cells die. So you have less than 3,000 nerve cells per unit. If you treat the rats with 3 doses of our drug, the 3 green bars, the nerve cells do not die. And then we did the same in glaucoma with rats. You increase the pressure in the eye, the retina dies. So the blue bar on the right are the healthy neuronal cells in the retina of a rat that does not have glaucoma, and they're about 4,000. If we increase the pressure in the eye, half the nerve cells die, and if we treat with our drug, the nerve cells don't die. So we have shown in 2 different models that our drug protects nerve cells from dying. That means it is disease-modifying. Axonal transport is symptomatic. Nerve cell death is disease-modifying. Now, we have shown both symptomatic and disease-modifying efficacy in animals. We have shown it in 8 different animal models. And so in animals, I'm very confident of saying that the drug is symptomatic and disease-modifying. But what do we have in humans? Now, we have done 12 studies in humans, a number of studies, smaller studies in healthy volunteers, because the FDA wants you to do that, and then 2 small studies in early Alzheimer patients, 1 large study in Alzheimer patients, and right now we are in a very large study in 760 early Alzheimer patients that will last 18 months. And then we did 2 studies in Parkinson's, a small one and a large one. I'm going to talk exclusively about cognition, as I already mentioned before, because then we can compare with the rest of all cognitive drugs. And the 2 small Alzheimer's studies we did show in very few patients, in 5 and 9 patients, that our drug is much better than placebo. In fact, it is statistically significant from baseline. If we combine those 5 and 9 patients, we get 14 patients, and that number is highly statistically significant from baseline. And as you can see, quite better, 3 times better than placebo. Want to point out that the improvement in cognition is 3.5 to 4.5 ADS-Cog points. That's very high. Of course, these are tiny studies, and maybe we just lucked out. So we did a bigger study, 350 patients, 3 doses plus placebo, endpoints for ADS-Cog and CGIC, and it was a 3-month study. And when we looked at the ITT population, unfortunately, placebo was just as good as everything else. So we did not meet primary endpoint. However, when we did subdivide the patients into early and advanced moderate, we saw that the moderate early showed a beautiful, highly statistical dose response curve. That's what you see on the right. And in fact, again, the ADS-Cog improvement is 3.5 points. So it's exactly the same as the one we saw in the two small studies. So this is very encouraging, but we wanted to make sure we were not cherry picking because it is a subgroup. And we did a forest plot. The forest plot shows clearly that it works in every single population that we tested it in, be that age, be that female or male, be that heavy or light, be that on drugs or not drugs. I want to point out that this drug actually works on top of existing therapy, on top of the symptomatic therapy. It works on top of antidepressants, and it works if no drugs were used. Also want to point out that it works in ApoE4 positive patients and in ApoE4 negative patients. And then it works in every race we tested. So let me quickly switch to Parkinson's disease. I just showed you that our drug works in 5 patients, 9 patients, 100 patients, and here in 523 patients in cognition. In the whole ITT population in Parkinson's, we actually saw that placebo got worse, and our drug fully recovered cognition. When we then looked at Parkinson's patients, we see that placebo gets a lot worse, and our 2 doses recover cognition. I need to point out that the 1.7 points in MMSE you see here corresponds to about 3.5 points in ADS-Cog. So we are back at the 3.5 points to 4 points ADS-Cog improvement. Again, we did a forest plot because we wanted to make sure we were not cherry picking, and the forest plot shows what we wanted to see. It works in everything tested. We also did biomarkers. We could show that in neurofilament light, which is a marker that shows nerve cell health, the higher neurofilament light, the more sick the nerve cells. We saw that, in fact, it improves health. We showed in 3 different inflammatory factors, GFAP, IL-5, and IL-4, that the drugs reverses and lowers inflammation. And then we saw in 2 neurotoxic aggregating proteins that it lowers them. And this goes back to the landscape. I'm putting together here what all the drugs on the market do and how our drug compares to them. So the green line at the bottom is the normal cognitive decay of a person that does not take any drugs or a person that is on placebo. The red line is Aricept. This is from Aricept literature. It improves cognition by 1.5 points at 3 to 6 months, and then it stops. The activity goes away. At 9 months, Aricept has no activity. The blue line is Kisunla and Leqembi. Again, this is from their publications. This is from the Biogen and the Eisai and Lilly publication. What they do, they don't improve cognition, but they improve the cognitive decline, and interestingly enough, by about 1.5 points, the same amount that Aricept improves it above baseline. So at 18 months, the patients get 1.5 points less demented than if they were on nothing. And then the purple is us. And what I can show or say with confidence is that at 3 months, we have a 3 to 4 point improvement in ADS-Cog. After that, I'm not sure. But given the mechanism of action, we believe that buntanetap is disease modifying, and therefore will have a different slope than the natural disease progression. And that is why we are doing an 18-month study to prove that. So this is the study we discussed with the FDA and they approved. It is an 18-month study. It is in the exact same patient population where we saw the positive dose response curve. So it's early Alzheimer patients. They show the 3.5-point improvement, and it's the same dose, the same patient population. They're p-tau tested, so we make sure they have Alzheimer's, and they are MMSE 21 to 28, so we make sure they're in the right dementia population. And basically, we agreed with the FDA that we can do a dual study in the same study. At 6 months, we can open the blind, and we can actually file an NDA for short-term if the data is good. The study continues blinded for an additional 12 months, and we can file an NDA for disease modification if the study is good. By the end of next year, we should have the NDA for the 6 months, and by the end of 2027, we should have the NDA for the 18 months. This is exactly the study. It's 760 patients, 30 mg and placebo. The endpoints, we have 2 types of endpoints. For symptomatic, we have ADAS-Cog11 and ADCS-CGIC, or IADL, sorry. And for disease modification, we have volumetric MRI and biomarkers. So at 6 months, the first 2 biomarkers will be important. At 18 months, all 4 endpoints will be important. I just want to close with the patents. The ones that have known ANVS for a little while know that we have been around for a while, so the patents are getting old. And we were lucky because last year we came up with a novel crystal form that prolongs our patent life of everything from composition of matter to all the different patent families. And we have a total of 13 patent families for everything all the way to 2044. And thank you very much. Questions?